All right, so we're in section 10.8, last section of chapter 10. Hello, Mr. Tolbert.
See how many mine did you have?
So geometric probability. Let's have a quick reminder on how, got a big picture idea of probability. So the way I think of probability, no matter how we're working with it, and we talked about this way back at the beginning of the year, we said that the probability was, the way we find it, big picture, is favorable outcomes divided by the total outcomes. And the way I always think about probability in general is just favorable over total. We're always looking for favorable over total. Our probability always gives us a decimal or a fraction. Between 0 and 1. So our probability always comes out between 0 and 1. What does a probability of 0 tell us? What does that mean? It can't happen. It's impossible. It can't happen. And a probability of 1 means guaranteed. It's certain. It has to happen. And if we convert these to percentages, we can convert our fractions or decimals to percentages, and our percentages would come out between 0 and 100%. So that's a way to check if you made a mistake. If you get a probability of 325%, you know you've made a mistake. There's something wrong. So we always get a decimal or fraction between 0 and 1. When we convert that to percent, it's between 0 and 100%. 0 says it can't happen, and 1 says it is certain to happen. It has to happen. All right, so we're going to talk about probability, and we're talking about probability in the middle of the area unit. We're going to talk about how we use length to figure out probability, and how we use area to figure out probability. That's what this whole section is about. So let's look about length. Really easy idea with length. So what we're going to do when we're talking about probability with length is we're on a segment. On a segment, our probability is going to be the favorable length divided by the total length. And this formula, this should be one of the formulas that you put in your circle for geometric probability. You could say on a segment, your probability equals favorable length over total length. So let's look at a couple of examples of using this idea. So here's my segment. I'm going to make a segment here, and we're going to make the segment go from 4. So it's going to be 5, 6, 7, 11, 12, 13, 14. From 4 to 14. Actually, I want to do one more. I want to do 15. So the segment goes from 4 to 15. And that's going to be 0.6. And this is going to be 11. And I'm going to label some points here. F, G, H, and J. All right, we're going to pick a point at random. And we want the probability. So we're going to pick a point on the segment somewhere between 4 and 15, and we want the probability that the point is on the segment GH. So because we're on a segment, our probability is the favorable length over the total length. Favorable over total. So our favorable length is the length of segment GH. How long is segment GH? How far is it from 6 to 11? 5 units. I can count. 1, 2, 3. Did I mislabel my points? 6, 7, 8, 9, 10. Yeah, that should be H's. There. There's H. So GH is 5 units long. What's the total length? 11. So I could count from 4 to 15. The other way I could do this is the same as doing 11 minus 6 over 15 minus 4. So I take the big minus the small, that tells me the length. So my probability is 5 over 11. That if I picked a point at random on this segment, that the point would be on segment GH. So that's all there is to it. And it could be any point. It doesn't have to be an integer. It doesn't have to be 1, 2, 3, 4, 5. It could be 7.77832. Any point. My probability that I get a point that's on segment GH is 5 out of 11. Favorable length over the total. All right, are we good on that example? So the next one we'll do, the problem sounds kind of complicated. But if we turn it into one of these length problems, it's actually really easy. So for this one, we have a ship. It crosses a river every 40 minutes. And we're not going to count, we're not going to worry about the time it takes for the ship to turn around, time for it to load and unload. We say it gets there and leaves every 40 minutes. We want the probability. We're going to show up at the station at a random time. The probability that we have to wait 25 or more minutes. So we show up at the station at a random time, and we want the probability that we have to wait 25 or more minutes. So just looking at this looks like it could be a kind of a complicated problem. But what we're going to do is turn it into a problem that has to do with a segment. So I'm going to draw a segment. And I'm going to count my minutes by 5, since we're talking about 25 here. So there's 0. So this would be we arrived at the station right as the ship is leaving. And then I'm going to do 5, 10, 15, 20, 30, 35, 40. So there's 40. So if we arrive right when the ship is leaving, we wait 0 minutes, and then if we If we arrive right when it's already left, we wait 40 minutes. So here's my segment, and we're going to say that the ship, so we're arriving sometime after the ship has left, and the ship's going to leave again at this end of the segment. So where on this segment am I going to have to wait for more than 25 minutes? Well, if I arrive here, how long am I going to have to wait? 5 minutes. If I arrive here, I wait 10, 15, 20, 25. So if I arrive anywhere in here, I'm going to wait 25 or more minutes. If I arrive right here at the 15 mark, I have to wait exactly 25 minutes until the ship leaves again. Anywhere over here, I'm going to wait more than 25 minutes. And that's what it said, 25 or more. So our probability is the favorable over the total. And here our favorable is waiting 25 or more minutes. Doesn't necessarily mean it's a good thing. It's just the thing that we're interested in. So how long is our favorable segment where we're waiting 25 or more minutes? What's the length of the segment where we wait 25 or more minutes? 15. What's the total length of the segment? The whole thing? 40. And I can reduce that fraction, 15 over 40, reduces to divide everything by 5, 3/8. So I have about a 3/8 chance. I have a 3/8 chance that I have to wait 25 or more minutes arriving at the station at any random time. All right, are we good there? So this problem that sounds difficult, when we turn it into this problem with a segment, set it up as a segment, turns out to be pretty easy. All right, we also want to talk about how we use area and probability. So this is very similar to what we just talked about. Area and probability is, we would use that if we're talking about like a dartboard or something. We're throwing a dart at a dartboard. What's the chances that we hit a particular part of the dartboard? It has to do with the areas that we're talking about. So when we're talking about area, our probability, and this would be what goes in your circle, your formula goes in your circle for geometric probability, is the favorable area divided by the total area. So the favorable area is the area of the thing that we're interested in, and the total area is going to be the area of the entire thing, the entire shape, the entire target, whatever we're talking about. So that formula would be what would go in your graphic organizer. It's really the same idea. With segments we use length, area we use area. So let's look at a couple of examples of using area with probability. So I'm going to have a circle here and see if I can draw a decent picture. Came out pretty well last time. So we're going to put this circle perfectly inside a square. All right, that one turned out not too bad. So we're saying the circle fits perfectly inside the square. And we're going to say that the length, the side of the square, is 5 inches. We want the probability that if we toss a dart at this square, that we hit one of these shaded corner areas. So we're tossing a dart at random into the square. We want the probability of hitting the shaded part. So our probability is the favorable over the total, always. How do we find our favorable area? The favorable area of these little corner pieces? How do we find that favorable area? We're going to take the entire area of the square and we're going to subtract the area of the circle. We're getting rid of the area of the circle. So all we'll be left with is the area of the square. So our favorable, I'm going to write that in symbols, is the square minus the circle. And the total area, we're tossing our dart into the square. The total is just the area of the square. So let's find these areas. So our favorable is the area of the square. What's the area of the square? What, 5 times 5? 5 times 5 is 25. .25 square inches minus, I wanted to add one thing in, 5 times 5 minus the area of the circle. How do we find the area of this circle? We're talking about the area, so we just pi times, what's our formula for area of a circle? Pi r squared. What's the radius of this circle? What's that? 2.5. All the way across is 5 inches, halfway across is 2.5. So pi times 2.5 squared. So I get 25 minus, when I calculate this out, I get 19.635. And when I subtract that, I get 5.635. No, I did my subtraction wrong, didn't I? What should it be? 25 minus, double check my arithmetic here, 25 minus 19.635. I think this is right. 25 minus 19.635 is 5.635. That's what my calculator tells me. All right, so my favorable area is 5.635. The total area is the area of the square, 5 times 5. And this is square inches. So our probability is going to be the favorable area over the total area. 5.635 divided by 25, and when I calculate that out, I get 0.225 or 22.5%. So I have about a 22.5% chance when I toss a dart at the square of hitting these little corners. Questions on that example? All right, let's look at one more. This time we're going to talk about more of a normal target shape. So let me see if I can draw a decent picture here. Might not turn out perfect, but I think we'll get the. That's pretty good. Well, that didn't turn out too bad. All right, so there's my target. We're going to say the radius of the smallest circle is 2 inches. The radius of the second smallest circle, and we're talking about the entire radius, not part of it. The entire radius of this one is 4 inches, and the radius of the big circle here is 8 inches. And we want to figure out the probability of hitting the blue shaded ring. So we're tossing a dart, we're shooting an arrow, something at random into the target. So the probability of hitting the blue ring. Well, a probability is always the favorable divided by the total. Here we're talking about area, favorable area divided by the total area. How do we find what is the total area that we're talking about here? The area of what? The whole target, the big circle. The total area is pi times the radius of that big circle squared. So I get 64 pi square inches. I'm going to leave the pi in my answer. I'm going to write my answer in terms of pi because the nice thing happens right at the end. So the total area is 64 pi square inches. Our favorable area. How are we going to find our favorable area? We need the area of the entire blue circle, but we need to get rid of part of it. We need to get rid of the center part. So how do we get rid of that center part? Subtract it. So we're going to take the area of the 4-inch circle minus the 2-inch circle. So I'm going to write it kind of in symbols. So we're going to find the area of the 4-inch circle, subtract the area of the 2-inch circle. So let's do that. So that's going to be pi times 4 squared minus pi times 2 squared. 16 pi minus 4 pi. 16 pi minus 4 pi is what? 12 pi. Just like 16x minus 4x is 12x. 16 pi minus 4 pi is 12 pi. 12 pi square inches. So my probability is the favorable, 12 pi square inches, divided by the total area, 64 pi square inches. Pi divided by pi, those go away. Pi divided by pi is just 1, so those cancel. I get 12 sixteenths, and I can reduce 12 64ths. I was reducing one part and not the other part. 12 64ths. Reduce that, divide everything by 4. 3 sixteenths. And that comes out to 18 if I turn that into a percent, 18.75%. So I have an 18.75% chance of hitting that blue ring if I throw a dart at random into that target. All right, we good there? Okay. Homework. do the homework, and then we'll talk about our homework from last time. All right, there we go.